So far, we have been considering circuits where we have only a power supply or a battery and a resistor. Now we consider RC circuits. That is when we add a new circuit element, which is a capacitor now, to the circuit. Okay? So RC circuits refers to circuits where we have a resistor and a capacitor as circuit elements, in addition, of course, to the power supply. Now, let's consider the charging process of a capacitor. So consider this configuration here, where you have a capacitor, you have a power supply, and you have a resistor. Initially, the switch is in this situation, so this circuit is an open circuit and no current is flowing in the circuit. Now, if you bring the switch to position A, then in this case you get, which is here, then in this case you see this circuit is closed, and so the power supply is a part of this circuit, which contains now a capacitor and a resistor. Once this closed charge electric field is established in the circuit, and current starts to flow in the circuit, and as the current flows in the circuit, charge starts to get deposited on the plates of a capacitor. So the capacitor starts to get charged. This is called the charging circuit of a capacitor. On the other hand, a discharging circuit is assume that you have a capacitor which is charged now, that there is a charge across the plates. If you bring this switch to position B here, then in this case this electromotive force is out, and you have only a capacitor and a resistor in this closed circuit. And in this case, the charge flows from the positive terminal to the negative terminal, or the positive plate to the negative plate of the capacitor across the resistor. So this is a discharging circuit of a resistor, where the charge in the resistor discharges across a capacitor. There is no power supply in this circuit. Okay, the power supply is out now. Okay, so this is a discharging circuit. This is a charging circuit. Now we will analyze, of course, each of these circuits independently and see how the current, what is the current in each circuit, and what is the charge, and all of these parameters. So let's start with the charging circuit, which is this circuit here. Now, the important thing is that distinguishes RC circuits from only R circuits is that in RC circuits, that is when capacitor is involved in the circuit, then the current flowing in the circuit is a function of time. It varies with time. It's not constant in time. Okay, we will immediately see why. But this is an important feature of RC circuits. The current varies with time. Okay, so keep this in mind all the time. And how to see this? Let's consider that we have this circuit, and at some instant of time, current has been flowing for a while, and so there were some charge accumulated across the capacitor here. Okay. Now, when there is a charge across the capacitor, there is a potential difference across the capacitor, and we know that the potential difference across the capacitor is Q divided by C. Q is the charge at a given instant of time that had accumulated already on the capacitor. Okay, and it might be, we take it as the positive charge, but we know if we have a plus Q here, we have a minus Q here on the capacitor. So this is the potential difference across the capacitor. So we have a potential difference across the capacitor. Now, and there is a current flowing in the circuit as well. Okay, the current in this case, if you look at the electromotive force in this case, because this is the source of the electric field, then the current will be flowing from, because it's a single electromotive force, it will be from the positive terminal to the negative terminal in the circuit, and so it will be flowing counterclockwise. So this is the direction of the current in the resistor. Okay, now we apply the Kirchhoff loop rule to this loop. This is a single loop, and if you start, for example, from this point and come back again to this point, then in this case you will have plus E, and you move, there are no circuit elements until you come here. Here you are moving across the capacitor from the positive plate to the negative plate. So you are moving along the electric field lines, and this is a potential drop. So minus Q over C, okay? And then you are crossing the resistor along the direction of the flow of current, so minus IR. You're coming back to the same point, so this whole thing should be equal to 0. So the sum of the potential differences across the three circuit elements, the E, the C, and the R, should add up to 0. Okay, so this is what does say. Now, from here, actually, from this equation, we can immediately understand why the current in the circuit should change with time, and in particular, why it should decrease with time. Because evidently, as time passes, more and more charge will build up on the capacitor. But this minus this minus this should be equal to 0. So as this grows larger, this thing should grow smaller. Okay? And since R is constant, the only way that this could grow smaller or get smaller is to have I becoming smaller and smaller and smaller. Okay? So that's why this is. Because, you know, take these, if you want to think of it, take these to the other side. So E is equal Q over C plus IR. E is equal. E is constant. It's the electromotive force of the battery. Okay? And so this is equal, E is equal Q over C plus IR. As Q becomes larger, definitely IR should become smaller, so that to keep the equality. And since R is constant, then I is getting smaller. So whenever you are charging a capacitor, as time passes, in other words, physically, as more charge is builds up on the capacitor, on the place of the capacitor, the current in the circuit starts to drop. Of course, how far can it go? How much can it drop? Well, it will eventually get to 0. That's the smallest possible value that it can have. Okay? So when you eventually, when that current becomes 0, this is the smallest value that it can has, because it will, as charge gets, as Q gets larger, I should go down, it gets smaller. So how small can it get? It can get as small as 0 only. So as this gets to 0, then in this case, there is no more current flowing in the circuit. No more current flowing in the circuit, there is no more accumulation of charge on the capacitor, because there is no current to bring charge to the capacitor plates. Okay? So in this case, I actually becomes 0 when the capacitor is fully charged. Capacitor is fully charged, it has taken the maximum charge that it can take at that electromotive force, because the decisive factor here is E. Okay? So for that E, when the capacitor is fully charged, the current drops to 0, and that charge on the capacitor is the maximum charge. Let's look at that more closely. Let's first start with the other limit. That's at t equals 0, when the time equal to 0. In other words, just the moment you close the switch. In this case, there is still no charge at all on the plates of the capacitor. And so the potential difference across the plates of the capacitor in this case is just 0. Okay? So the equation in this case becomes E minus IR equal to 0. So Q over C here doesn't exist. So the capacitor, we say in this case, the capacitor acts like, at t equals 0, just when you close the switch, we say that the capacitor acts like a short circuit, as if there is nothing here. Okay? Why? Because there is nothing here as far as potential is concerned, because there is no charge yet on the plates of the capacitor, so there is no potential difference across it. So moving from here to here is like moving from here to here. There is nothing here. And so it's like just a short circuit. There is no circuit element. There is no potential drop across it. This is the meaning of a short circuit. So in this case, if this doesn't exist, then I is just E over R, and we write it as IE. I here, the small I here means initial. So this is the initial current, or I0 sometimes we use it. This is the current at t equals 0, just once you close the switch and before the capacitor charge starts to build up on the capacitor. That's the initial current, the current at t equal 0. Now, at t goes to infinity, as we have seen, that's after a long time, when charge built up continued to build up and a long time has passed, so that the current now, charge increases or starts to decrease until it reaches 0, then in this case we call that time infinity. Of course, there's nothing infinite in physics actually in this sense, but it is a long time, long compared to what we will see shortly. But after a long time, after the capacitor has been fully charged in this case, then the I is equal to 0. What is the consequence of this? When this is 0, then we have E minus Q over C equal to 0. So E equals Q over C. But this Q, we replace it now with Q maximum, because what is this Q? It's not any Q, it's the maximum Q that can be achieved at this E. So we have this equation in this case, at T equals infinity. That is, the maximum charge that appears on the capacitor in this case will be just C times E, CE. Okay? So as you can see, the maximum charge that appears on the capacitor in a given circuit depends on two things. It doesn't depend on R, it depends upon the electromotive force and the capacitance. Okay? So for a given capacitor, if you connect it to a larger battery which gives higher electromotive force, you can store more charge. If you want to store more, even increase the potential of the electromotive force of the battery, and so on. Okay? So that's this is the maximum charge that can be stored in a capacitor. And this is achieved when, after a long time, and at that time when that is achieved, the current in this case, in this capacitor, drops to 0. Now, having found the limits, I mean, what is the current at T equal to 0? What is the current at T equal infinity? What is the charge at T equals 0? It is 0. The capacitor, what's charge at T equals infinity? It's a Q maximum. But we don't know how does the current go, what is the functional form of the current when it decreases from I0 to 0, or what is the functional form of the charge. As functional form mean how does the charge or vary with time when going from Q equals 0 to Q maximum. The functional form of I mean I don't know how does I vary with time when it goes from I0 up to 0. Does it go linearly, quadratically? How does it vary with time? How does it drop with time? Okay, in what form? Now we can find this. Okay, and for this first we find how does Q changes on the capacitor changes with time, and by taking its derivative we can find, because the derivative of Q is just I, we can find how does I vary in time. And to do this, we first note that this equation actually, which is, we got it from the Kirchhoff's loop rule, is actually a differential equation. Why is it a differential equation? Where's the derivative? Well, I here is just dq by dt. I is dq by dt. And sure, therefore, it is a differential equation in Q. So if you substitute for I here dq by dt, you forget the differential equation, and we call this first order differential equation. This is integrable. It's very easy to integrate that equation. You just need to make some arrangements. Okay, so it becomes dq by dt equals to this. And now take the q terms to one side, so it becomes dq over, this is q term, and the d part here. Okay, q is a function of t. Now we can integrate this over dq, we can integrate this over t. And you integrate this over q, because q is the variable now, and this goes from 0, because when you start the switch, the minimum value of q is 0, and you create it, you want to find q at any instant, so you integrate it up to any q. The time goes from t equals 0 to any time. I want to find the behavior of the charge at any instant of time. So I integrate this from 0 to t. This is a len, this is just a t, and if you apply the limits, you get this equation. Len, this expression is equal to this, and therefore e to minus t over rc is equal to this expression in the bracket, and arranging, you get this expression. You get q of t, q varying with time, is equal to ce bracket 1 minus e to minus t over rc, and this ce is what we have just found to be equal q maximum. So this is how q increases in time. Look, at t equals 0, e to minus e to 0 is 1, so this whole thing is 0, as we expect. Q at t equals 0 is just 0. And at t equals infinity, at very large time, e to minus infinity, this is 1 over e infinity, which is 0. So it becomes Q becomes CE, which is the Q maximum. And in between, it grows, okay, according to this expression. So it's an exponential growth, okay. Now, what about the current? Well, the current is the time derivative of Q. So if you take the time derivative of this, the time derivative of the one is 0. The time derivative of the exponential is just minus 1 over RC e to minus TRC. And because I have CE, then this reduces to this expression. So I of t changes, has this functional form. Yani I changes with time according to this. Now this is an exponential drop. As you can see, at t equals 0, this exponential is 1. So I is equal E over R, as we have just seen, which is the initial current, the current at t equals 0. And as t goes to infinity, this thing becomes 0. E to minus infinity is 0. And so the whole thing becomes 0, and I indeed becomes 0. So I drops from 0, from E over R to 0, according to this functional form. So this is an exponential drop. This is characteristic of any RC circuit. This is how it drops. Now, this is how they look. If you start with the look at the current, for example, the current, as you can see, E to minus T of RC, it's here. This value here is I initial, which is E over R, and here it goes to 0 and it drops this way. If you plot it, this is the E to minus T over RC. Okay. For the charge, this is how it builds up. Okay. Starts CE, starts from 0 and ended up at CE. So as you can see here, at t equals 0, it's 0. Then it starts to build up first very quickly, then it slows a bit down, and this is called something like exponential growth. The maximum value here, which it achieved it for a long time, is CE. Now there is, as you have noted probably, there is an important factor here, which is RC, that appears actually in both the expression for the time dependence of the charge and the current. This is called the RC, and it is called the time constant of the circuit. It is determined by the product of the resistance and the capacitance. So it's a physical quantity that reflects the circuit elements that are present in the circuit, which are the current, the resistance, and the capacitance. Now, of course, the exponential here is dimensionless. This quantity is dimensionless, as should be in any exponential. And so RC should have units of time. It's interesting, but an exercise to check that really the product of resistance and capacitance will have units of time. Now, this quantity, tau, sometimes we refer to it as tau, or RC, is called the time constant of the circuit. Is going to the time constant of the circuit. Any circuit, the behavior of the current in a given circuit actually is determined by the product of the resistance in that circuit multiplied by the capacitance. Okay, so our circuit is an important parameter actually that determines the behavior of the current and the charge in the circuit. What do you mean by that behavior? More precisely, it actually tells us how fast does a capacitor charge or discharge. Okay, actually it is RC is what determines this. To see this, to see how does this do so, let's look at the current first. Okay, IT is equal, this curve is just a plot of this function. If you plot this function, this is what I get. At t equals 0, it is E over R, which is I, and then it ends up at 0. Now, when t, this is the time. When t is equal to RC, yani when RC minutes or seconds have passed, then this quantity becomes E to minus 1. E to minus 1 is 1 over E. E is a number. It's the base of the natural logarithm. E is 2 point something. Okay? So 1 over E is a number. And actually, it is 0.37, roughly 0.37. So when t is equal 1 time constant, that's just after 1 time constant, after RC seconds, the current here is equal 0.37 times the initial current. That's here. Sorry, here. So after one time constant has elapsed, after one time constant of seconds has elapsed, okay, the current drops to 0.37 of its values. Two time constants, when t is twice RC, then it drops to 0.135 of its value. When it's three time constant, it's even smaller and smaller. Okay, so and this is general. So if the time constant is small, then in this case the current drops very quickly to 0.37 of its value, and then 0.135, and then immediately to zero. But you know, the current dropping to zero quickly means the capacitor has charged already, because the current goes to zero when the capacitor is fully charged. Okay, so if you have small RCs, then in this case the capacitor charges very quickly. Okay, well, this goes, of course, this makes sense, because small c in particular means that small r means in general you will have a high initial current, and also small c's will have will need you know, together, when you multiply them together, you will get a small quantities, and probably you need less charge until you reach that potential. Anyway, so that's the meaning of the RC. Actually, it's a characteristic of any RC circuits, and it tells you how fast does it charge, or as we will see, discharge. What about the charge? The same applies here. This is the behavior of the charge as a function of time in any RC circuit, and this is a plot of this function. So this is, so when t, after the elapse of one RC, that's one time constant, yani one RC seconds, this quantity again is what? Is e to minus 1, and e to minus 1 is 0.37. 1 minus 0.37 is 0.63, or 63%. So actually, this expression becomes 0.63 CE. CE is Q maximum. So after the elapse of one times constant, the charge 0.63 or 63% of the maximum charge of the capacitance has already built up on the capacitor. So if this time constant is small, this happens very soon. If it's large, this takes longer time. So as you can see, so it takes larger time now to charge the capacitor if tau is large, okay? Because as you will see, it will reach just 0.63% later, and then this 0.86 after 2 taus later, and so on and so forth. So it will generally take longer time for the charge to accumulate to reach the maximum charge on the capacitor if tau is large. Because if it's large, then this will not achieve it here, but it will come, it will not just rise up here to this point very quickly, but it will rise up this way. And so it will take longer time until it charges. Okay? So this is the meaning of the time constant of an RC circuit. Now, capacitor, when it accumulates charge, it's also storing energy. Okay? And we know what is the energy stored in a capacitor actually. And to express this in terms, to find what is an expression for the energy stored in a capacitor after it's fully charged, we first recall that the relation Q maximum equals CE. If you multiply both sides by E, I mean, we know that Q maximum is equal CE. If you multiply both sides by E, then you got QE equals C squared. Divide by 2, the left-hand side is 1/2 Q maximum times E. E is what? E is the potential difference across the battery. But it's also the potential difference across the capacitor when the capacitor is fully charged, because there is no current, no more current in the resistance, as we have seen. Okay? And so therefore, this quantity is 1/2 the maximum, the charge on the capacitor, fully charged capacitor, multiplied by the potential difference across that capacitor, which is the same as the potential difference across the battery. So this is the energy stored in the capacitor, and this is equal to 1/2 CE. E square. Okay, this is the energy expression for the energy stored in a fully charged capacitor connected to an electromotive force of magnitude E. So this is the energy stored in a fully charged capacitor.